Good afternoon to all of you. We wish to see what is equilibrium of a particle and a system of particles. First of all, let us try to understand what is a particle. A particle is represented by a point. Now, any body has got dimensions, shape, size, etc. So, if you are representing it by a point, there must be certain physical significance to that. Let us see what that is. If you take a point can only translate, that is, move about from one place to another, get displaced from one point to another point. But there is no rotation of a particle about an axis passing through itself. The particle is so small that we ignore any rotation of the particle about an axis passing through itself. Whereas if you take a system of particles, we cannot ignore rotation. So a single particle can only translate. It has only pure translation. Whereas a system of particles can translate, can have pure translation, can have pure rotation, or it can be a combination of pure translation and rotation. For example, if I have a ball and I threw it towards you without rotating it. Now every particle on the ball will have a parabolic path. All these parabolae are going to be parallel. Parabolic paths will be parallel, and this is a case of curvilinear translation. The path is curved. We can even have rectilinear translation where the paths are straight lines, parallel straight lines. So these are curved parallel lines. Now I can take the ball and spin it on my finger like that. So that is pure rotation. Or I can spin it and throw it towards you. So there will be rotation as well as translation. Or I could roll it down on the floor. That would again be combination of translation and rotation. Now, if you take the earth, if you treat the earth as a particle, then what it means is we are ignoring the rotation of the earth about its own axis, and we are considering only the earth's revolution around the sun. On the other hand, if you consider the earth as a system of particles, you cannot ignore the rotation about its axis. Then if you take a point on the earth, that point on the earth would be moving like this around the sun. This would be the path. A particle is said to be in equilibrium if the net force on it is zero. When the net force on a particle is zero, the particle can be in two states. It can either be at rest, then it is called a static equilibrium, or it can be moving at constant velocity, then it is called dynamic equilibrium. If you consider a disk, supposing this is a disk, and I apply two forces F and F like that on a disk. A disk is a system of particles. This disk will not rotate because if you take the torque of these two forces about the center of mass of the disk, they will cancel each other. So there will be no torque. On the other hand, the disk will translate. On the other hand, the disk can translate. So it is in rotational equilibrium but not in translational equilibrium. If you took the disk and applied two forces like this, a couple, the net force is zero, but the net torque is not zero. So it is in translational equilibrium but not in rotational equilibrium. If you had the disk and let us say I had applied force F1 and F2 and F2 was greater than F1, then the disk would translate towards the right, but the torque of F2 will overpower the torque of F1 and it will rotate in the anti-clockwise sense while translating. So it is the case of combined rotation and translation. If you take the example of the earth again, if you see the earth is going around the orbit which is nearly circular. The centripetal force is provided by the attraction of the sun on the earth. Because the earth is translating in a circular orbit and there is a force acting on it, there is a net force on it, it is not in translational equilibrium. On the other hand, this force passes through the center of mass of the earth, hence it does not create any torque. So the net torque on the earth is zero. Therefore, the earth is in rotational equilibrium. However, it must be noted that this rotational equilibrium is dynamic because the earth is rotating at a constant angular velocity of 2 pi radians per 24 hours. Just as when we say that when a body is moving at constant velocity, the net force is zero. Similarly, when the net torque is zero, the body could be rotating at constant angular velocity. So therefore, the earth is in dynamic rotational equilibrium and it is not in translational equilibrium. The next thing we would like to see is that equilibrium can be of three types: stable, unstable and neutral. Let us try to understand these with a diagram. Supposing I drew a hill, a valley and a plain. Supposing I have a particle here and I disturb it, I bring it here, I disturb it like that. If I did that, it will not regain its original position, it will fall off and not get back to its original position. Whereas if I had a particle here, if I displaced it slightly here like that, it would get back. It would have a tendency to go back to the original position. Here, if I displace it by a certain amount, it will stay where it is. It will neither have a tendency to get back to the original position nor move away from it. So, this equilibrium is called as unstable. The net force is zero, but when you disturb it, it does not get back to the original position. This is the case of stable equilibrium, where the body has a tendency to get back to its original position when disturbed, and this is the case of neutral equilibrium. Now, what you can observe here is that when the equilibrium is unstable, the potential energy is maximum, and when you disturb the body, the potential energy decreases and it continues to decrease. That is, it doesn't come back to its original position. In the case of stable equilibrium, the potential energy is minimum. When you disturb it, the potential energy increases and the system has a tendency to get back to its original position. In the case of neutral equilibrium, the potential energy is constant. It neither increases nor decreases when you disturb it. Now, what you must note that in the case of stable equilibrium, when you disturb it, the particle oscillates about a mean position or the center of oscillation. This is the mean position or center of oscillation. So, when a particle oscillates, the mean position or center of oscillation is always a position of stable equilibrium. Let us take another example. Supposing I have a rod and the rod is pivoted about this point and I displace it like that. I bring it like that and I leave it. Well, it will get back to its original position. The rod is an example of a system of particles. Here we talked about the stability of a particle. Here we are going to talk about the stability of a system of particles. So, since it has a tendency to get back, this is the case of stable equilibrium. You can see the center of mass has risen. So, the potential energy is actually increased. So, it is a similar case of a valley as in the case of a valley. So, this is the case of stable equilibrium and it would oscillate. Supposing the rod were kept like this and the pivot were like that, let us say you disturb it slightly this way. Let us say this angle is say some 10 degrees, you displace by 10 degrees and leave it. Will it get back? Obviously not, it will not. It will come down and get back to this point where this is also 10 degrees. So it's going to have an angular oscillation of on either side of the vertical, but it will not get back to the original position. So here again you see that the oscillation is about the stable equilibrium position. This is the stable equilibrium position. It is about this stable equilibrium position that the oscillation takes place, not about the unstable equilibrium position. Again, as an example, supposing there is a rod which is pivoted at its center. Now let us say I displace it and leave it. If I displace it and leave it, it will stay where it is because the net torque on the system is 0. Where in any position the net torque is 0. So the potential, when I displace it, the center of mass is remaining, is neither rises nor falls. So there is no change in the potential energy. So this is the case of neutral equilibrium. Thank you.